I am now going to go back on some of the exam questions we discussed in the last unit, which we could not complete because we hadn't a mole done. You're now in a position to deal with this, and look at the first question here. I'm reminding you again now, just please make a note of the year in each case. This is 2009, question 10a. Right, and you were able to do all the first parts. Let me just develop them a little further for you again now to see are they okay. State Avogadro's law, equal volumes of all gases under the same conditions of temperature and pressure contain the same number of particles, okay? Same number of atoms or molecules, okay. Give two assumptions of the kinetic theory, you're okay with that, okay? Constant random motion, no attractive forces, occupying no space, okay? And give two reasons why real gases deviate from ideal behavior. Real gases deviate because their particles occupy some space and because there are attractive forces between them, van der Waals, dipole-dipole, or hydrogen bonding. And here's the bit we couldn't do. How many moles of gas are present in a sample containing 1.8 by 10 to the power of 24 atoms of chlorine at STP? So you're asked how many moles are there in that. Now be very careful. 1.8 by 10 to the power of 24 atoms of chlorine, right? And they've written it as CHLORINE. They're being deliberate there now for some reason. Chlorine at STP. Now be careful, okay? How many moles of gas are present? That many atoms of chlorine. If you have that many atoms of chlorine, which is Cl, be careful, atoms. Okay, atoms of chlorine, then you have, of course, got to divide by 2, 0.9 by 10 to the power of 24 molecules of chlorine. And it says at STP. I better remind you of that, at STP. Now, do you see the trick in that question? They're very unfair there now, very unfair, but they want to see how well you understand this. How many atoms are there in that, okay? How many moles in that many atoms of chlorine? That many atoms of chlorine has half that number of molecules because chlorine gas is diatomic. In other words, did you know that that's chlorine gas? That's what they've asked you. You either did or you didn't, okay? And that's what you're at there, nothing more to it than that. Cl2, very good. Okay, so that is your molecules, and so you're back to your mole box now. I have particles, and they are looking for moles. So you divide by, in this case, you have particles, 0.9 by 10 to the power of 24, divided by 6 by 10 to the power of 23, and that will give you your value. And that's what you want, nothing more, nothing less than that. That's all you're looking for. And that should be okay, right? You have the general gist of that, okay? I'm going to say no more to you. That would be moles. Run that through your calculator. Moles of Cl2 at STP. Now, they're playing with your head a little bit here, okay? They're playing with your head. They gave you particles, and they wanted, in this case, moles. You never had to go to volume. And the STP could tempt people into using 22.4. Think for a minute, okay? The only reason they said that is to tell you that chlorine is a gas. That's the only reason they said that to you, okay? So that's actually the answer, okay? Do you need to be told any more on that? Okay, just evaluate that, run that through your calculator, and you get moles, right? And you're fine. I'm going to leave that one. That was 2000. Okay, and very important that you're getting them right now. That's 2009. 2006, this one I showed you already too. Let me use it again, please. 2006, we're looking at this question down as far as here. We can't do all of this yet. I need to do some stoichiometry with you, but we can do some of it. What is an ideal gas? Here we go again. This is a gas which obeys all the assumptions of the kinetic theory under all conditions of temperature and pressure. Give one reason why a real gas, like carbon dioxide, deviates from ideal behavior. Deviates from ideal behavior. Okay? Gas particles take up space, and therefore they deviate from ideal behavior. Gas particles, like carbon dioxide, have intermolecular bonds called van der Waals forces, which deviates from ideal behavior. And that's the kind of thing you want more than anything else, and you just have to be aware of that. Okay? And that's fine. Okay? Next, assuming ideal behavior. Now watch the language there, please. Okay? You must be very careful. Assuming ideal behavior. How many moles of carbon dioxide are present in 720 centimeters cubed at a stated temperature and pressure. You can never have a volume of a gas without the temperature and the pressure being given, unless you're looking for one of them, and give your answer correct to one significant figure. Okay, how many moles? So here we go. Do you realize what you're being examined in here? Of course, this is your formula. PV equals nRT. And we're going to list our data. And they want moles N. Very good, okay? Now, basically, I list them for you just to make sure. V equals 720 centimeters cubed. Okay, the temperature happens to be 10 degrees Celsius. Okay, and the pressure happens to be, in this instance, 1 by 10 to the power of 5 pascals. Right? And you can see what you're working with. How many molecules? Okay, that's it. And they're asking you there how many moles. Now, we've done this already, but I want to just make sure you're okay. It's very important. R is equal to 8.3 available to you at the front of your exam paper. Okay, and you're looking for N. Is that okay? And you're looking for N. No problem there, except, you know what I'm going to say to you next? If you don't convert them to metric, you're in trouble. Okay, it must go to metric. That is going, in this case, 720 multiplied by 10 to the power of minus 6. Now, I realize that's not scientific notation, but it's the correct value. If you pop that to your calculator, it will take care of it for you. Don't worry about it, okay? That one will be, in this instance, you must go to Kelvin, 283 Kelvin. Okay, Kelvin. And pascals is okay. That's okay, and you're looking for that, so go and solve for N in that. Okay, and once you have that, you're on your way. There's no more to it. And so the number of moles comes out to be 0.03. 0.03. Okay, assuming ideal behavior, right there, carbon dioxide. N equals 0.03 moles of carbon dioxide. Okay, there is your answer. Please, a number, a unit, and a tag. Very important when you're doing that. All right, now it's the next bit I want to deal with. How many molecules of carbon dioxide are present in this quantity of carbon dioxide? Okay, this quantity of carbon dioxide. So basically you have moles and you want to know the number of molecules. You know, don't you? It is simply 0.03 multiplied by 6 by 10 to the power of 23 molecules. Molecules of carbon dioxide. Now, please, a number, a unit, and a tag every time, okay? And you'll be fine with that, okay? And that's 0.18, or if you want to go 1.8 by 10 to the power of 22, that'll be fine. Okay, that's it. Now, please be careful. It's not about numbers here now. It's about not making silly mistakes. Now, that kind of a question would be riddled with errors. I can't go any further with you now. I'm trying to show you the progression of chemistry here now that you must be very careful. I can't go any further now without dealing with a method in stoichiometry called reacting masses. They've now given you a full balanced chemical equation and they want you to take the number of moles there and there. What mass? Okay, the reaction of carbon dioxide and lime water is as follows. By the way, you'd be expected to know that for leaving cert anyway in the water section. What mass of calcium hydroxide is required to react completely with the quantity of carbon dioxide given above? So there you are. That's the quantity given above. You'll be going back to here to use that, but I need to do some stoichiometry with you to do that. So there's a question typically coming up in questions 10 and 11 where they don't examine just the topic, but they want to see, have you the syllabus covered? Have you all the other bits done? Whereas the main theme here now would have been gases and the mole. There was a little bit thrown in at the end on stoichiometry, and you must be careful with that. It's very important that you follow that up. Is that okay? And if you do that, there won't be any issue. The next question I'm looking at is 2005. Now, these will be reasonably straightforward. You won't have any issues with them, but I need you to see the extent to which they are being examined. Okay? The extent to which they're being examined. Now, I'm looking at 2005, question 11b. Now, the whole idea with question 10 and 11, of course, is that there's an element of choice in it, since you only have to do 2 parts. So you must always be looking at these questions. They're only 25 marks, but they give you a bit of flexibility that other questions don't give you. Look here, you're asked to define a mole of a substance, and here we go again. A mole is a quantity in chemistry which contains 6 by 10 to the power of 23 particles. Please tell me you know that the particles could be atoms, molecules, or ions. Okay, that would be our definition. State Avogadro's law again. Okay, there's only 4 laws there. The idea you wouldn't know them is unacceptable. Now, equal volumes of gases under the same conditions of temperature and pressure contain the same number of particles, right? And this last part now is the bit I want to deal with for 12 marks. A foil balloon has a capacity of 10 litres. How many atoms of helium occupy this balloon when it is filled with a 10% VV mixture of helium in air at room temperature? Now, there's a unit of concentration. It presumes you have some volumetric done, and this is what they try to do, have you the full course done. So they throw something in. That's literally what it means, 10% of it, okay? So let me talk to you about this then. You have a balloon, okay, and there's 10 litres in it, very good. 10% of that happens to be helium, okay? 10% of it is helium, okay? And ultimately that's it. Therefore, 10% of 10 litres equals 1 litre of helium. There's the important piece for you. Now, all the huffing and puffing was about that. You have 10 litres, filled with 10% VV mixture of helium, okay? Helium in air. So the other 90% is air, right? At room temperature and pressure. And they've asked you a simple question. How many atoms of helium occupy that? So you have a volume and you want particles. So you're straight into your mole box there, aren't you? So you have 10 litres of, you have 1 litre of helium, okay? And that's equal to, it tells you their room temperature and pressure, 1/24 moles of helium, and 1/24 multiplied by 6 by 10 to the power of 23 is going to be atoms of helium. Now, please, I do it all the time. I hope you do it all the time. Number, unit, and tag. Everywhere, please. That's very important. Do you realize that helium is a monatomic gas? All the members of group 18 in your periodic table, all members of it are all monatomic. They're all, you know, do you? I'm sure you do. They're all, they combine with nothing else. They're in group 18, okay? Will you be aware of that? And they're helium, argon are 2 common ones, right? And they don't join with anything, so they're on their own. If that happened to be, it's not. But if it happened to be carbon dioxide, do you understand? You'd have to allow for that. You'd have molecules here then, and you have to multiply by 3 to get atoms. Now be careful. What are you talking about is the very important thing here, okay? So that was helium. Just be careful with that as to how you go about it and you'll be fine. All right? Now, will you revisit all those questions, please, in your own time? They're all past exam questions in their own way, and you just need to keep familiar with them so that you'll be in a position to kind of work on them again. I've one last one here I'm going to look at now, and that will be it in this category. The category I'm talking about now is we're dealing with the mole still. This is 2007, and the question is 10B. 10B is what I'm looking at there, okay? The one with the fire extinguisher, right? And I want you to have some sense of that. 2007, question 10B. 2007, question 10B. Okay, and we're looking at that, right? State Avogadro's law is the first thing, and here we go again, right? Equal volumes of different gases under the same conditions of temperature and pressure contain the same number of particles. Carbon dioxide is stored under pressure in a liquid form in a fire extinguisher. 2 kilograms of carbon dioxide are released into the air as a gas on the discharge of the fire extinguisher. Okay, so 2 kilograms of the carbon dioxide is released into the air when you fire the extinguisher, right? What volume does this gas occupy at a pressure given and a temperature given? Okay, so that's it. They've given you 2 kilograms of carbon dioxide, 2 kg of carbon dioxide. First thing you must do is convert that to moles, of course, okay? So that's equal to 2,000 grams of carbon dioxide. You're all okay with that? That's what you want there, nothing more, nothing less than that. Just go and get that right and you have it, there'll be no issue, right? And you work from there then, right? So you take that and you must divide by, to get moles, are you all okay with what you're going to do? You'll divide by the relative molecular mass, 2,000 divided by 44. Am I right? Carbon dioxide 12 for carbon, and 2 16s is 44. Okay, so that's the number of moles you have, and that comes out to be, I better get an answer for you, it comes out to be 44.45. 45.45. It comes out as 45.45, yes. 45.45 moles of carbon dioxide. Now, please, I can't say it enough to you. Write it out in full. This is not maths, this is chemistry, okay? Very important. You have moles, right? And they want to know what volume does it have. I feel a formula coming on. Okay, we seem to have that. We have that. We have that. And we have that. And we're looking for that. Are you okay? Let me just go through the details. We don't need to do anything with it other than that's it. Okay, now always list your data. You'll eliminate error when you do that. That's not a waste of time. Okay, so I'll start there. I see the pressure happens to be 1 by 10 to the power of 5. P equals 1 by 10 to the power of 5 pascals. Pascals given to you there. That's a metric unit already. Okay, the temperature, to speed things up, they happen to give it to you in Kelvin. That's correct. 290 Kelvin. Okay, that's the temperature. The number of moles now is 45.45. No units for that, of course. And R is given to you, of course, on the paper 8.3. 8.3. And you are looking for V. V equals, okay? So you go and solve for V there. V is equal to nRT all over P. Now, please, everybody, it's very important that your units are right. When you write them like that, you're checking your units. Sometimes they need conversion, sometimes they don't. The examiner sometimes shortens the question by giving you the right units. It takes less time then to do it. But please, every time, it should be the same method all the time. You should never be varying from your method, and you'll do very well. Okay? And they've asked you here for the mass, so you must go and get what volume does the gas occupy? What volume does it occupy? And that's what you're going. And the volume comes out to be 1. The volume comes out to be 1.1. Will you be careful with this? When you solve for V here, it's equal to V equals 1.10. Do you know the units for that answer? Meters cubed. Now, the number of people that would write liters down there is frighteningly high. Don't be one of them, okay? Please, now, everything must be metric, and you'll get metric there. That's metric, that's metric. They're okay, that's metric already. There's no units of that, and so that has to come out. It has to come out in meters cubed. The only warning I have for you with that particular relationship is you must make sure that everything is metric. That's the one health warning going with that formula. I've mentioned it already to you now. Please be careful. You'll be raging with yourself if you make that mistake. That's the answer, and that's the volume they wanted, and everything is fine with that. Now, they're not finished the question yet. Sure, they're not, but that's what you've got there. Now they ask you, what mass of helium would occupy the same volume at the same temperature and pressure? And do you know, there's only 6 marked for it now, and that's often a good indicator. There won't be much to that. Okay, so what do you do in this instance? I'm sure you know, do you? That number of moles and multiply by the MR. Okay, because it's under the same conditions of temperature and pressure. There wasn't going to be much calculation on that. 45.45 multiplied by 4. Where did the 4 come from? 45.45 multiplied by 4 will be grams of helium. Where did that come from? That is the relative atomic mass of helium. Group 18 in your periodic table, printed on the front of your exam paper, and there's your answer. That is your answer, just multiply it out, okay? That is your answer, grams of helium. Now, that would be considered a challenging question. And if you're able to say to me now, you know, that's okay, I'm okay with that, then you have a high standard in chemistry. Don't be any doubt about that, okay? That's what you have there. What mass of helium gas would occupy the same volume at the same temperature and pressure? Give one reason why carbon dioxide is more easily liquefied than helium. Now, that's demanding enough. I'm going to ask you now to think about that for a second. More easily liquefied. I'm going to write it down here for you, okay? Give one reason why carbon dioxide easier easier to liquefy. Easier to liquefy. Will you be careful, please? Q-U-E-F-Y, yeah, liquefy. Okay, easier to liquefy. If it's easier to liquefy, do you know what that's a tough enough question now, and I want to tell you about it, that the error rate here will be very high. Okay, easier to liquefy than helium. When does a gas liquefy? And the answer is when you drop its temperature. Okay, there is the boiling point of a particular substance, and there is the melting point down here. Okay, if you have something that's a gas, the temperature of that substance is above its boiling point. And if you dropped its temperature, you'd eventually turn it into a liquid down here. And if you drop this temperature more into a freezer or whatever, you'd eventually turn it into a solid down here. So you have a gas up here, you have a liquid down here, and you have a solid there. So liquefaction occurs at the boiling point. Now, if carbon dioxide is easier to liquefy, do you see they're playing with your head there? You're dropping the temperature if you want to liquefy it. There's the gas, and you're dropping the temperature. It means that the carbon dioxide will turn into a liquid before helium will turn into a liquid. So its boiling point must be higher. You're dropping the temperature, and you will meet the boiling point of the substance that's easier to liquefy. So carbon dioxide has a higher boiling point than helium. Now, if they asked you, that would have been a very easy question. Okay, but you had to get that right. Okay, easier to liquefy means has higher boiling point. Has higher boiling point. That's what you're trying to develop, and I hope it's okay. And now I'm going to say that to you, that was the trick in that. Now, in its defense, it's only 3 marks, but at the same time, that's it. Now, what do you know about these two gases? And I'm again stressing to you now, this goes back to your chemical bonding. Whenever you mention melting point or boiling point in the lab, will you take it, please, that you're talking about intermolecular bonds? Okay, always. Something is more soluble than something has a higher boiling point, something has a lower freezing point or whatever melting point. Will you take it, please? One has a stronger interatomic bonds. It is easier. This one has this has a higher boiling point. Okay, so the bonds between those molecules must be higher than the bonds between those. That's right. Again, easier to liquefy means it has a higher boiling point. You're dropping the temperature to liquefy it, and you'll hit the boiling point of carbon dioxide before you'll hit the boiling point of helium. Okay, now it may be much lower, but I'm making the point one is higher. So why is that higher than that? It means basically with a higher boiling point, it means the molecules are held together with a stronger bond. Both of them have van der Waals forces. I'm not going to spell it in full now for you. Van der Waals and van der Waals. And the reason for that, of course, is, do you know, they're both non-polar molecules. There are van der Waals forces here and van der Waals forces here. That's a bigger molecule, and therefore the temporary dipoles would be stronger. Now that's getting a bit technical. I haven't it done with you. I'm only saying it to you that it would have been done some months ago. But basically, the intermolecular bonds, van der Waals, are stronger in carbon dioxide than that. And that's part of that in terms of what we're actually doing. Okay, now that is a series of questions on the mole that I needed to get through to show you the diverse nature of them. And it's vitally important that we would follow up on that now in relation to the relative molecular mass.